Tonight, we're going to confront a question that has haunted humanity since we first looked up at the stars. A question so profound that it challenges the very limits of human thought. What exists beyond the universe? Not beyond our planet, not beyond our galaxy, beyond everything. Beyond the farthest light that will ever reach us, beyond space itself. Here's what will keep you awake tonight. The observable universe stretches 93 billion light years across. But that's just what we can see. The actual universe might be so incomprehensibly larger that our entire observable cosmos is less than a single atom compared to an infinite ocean. And what lies in that ocean? Is it more universe? Is it nothing? Is it something our minds literally cannot comprehend? The answer might terrify you. Before we dive into the deepest mystery in all of existence, if you find these kinds of explorations fascinating, a quick like or subscribe would really help this channel grow. It's a small thing for you, but it means the world to me. Now, let's begin. Let's start with something that sounds simple, but is actually one of the most mind-bending concepts in all of cosmology. The observable universe. You've probably heard this term before. Scientists use it constantly when talking about space. But here's what most people don't realize. The observable universe isn't the entire universe. It's just the part we can see. And understanding why we can only see a portion of reality is the first step to understanding what might lie beyond everything we know. The observable universe has a diameter of about 93 billion light years. That's a number so enormous it essentially loses all meaning the moment you hear it. Let me try to give you some context. A light year is the distance light travels in 1 year, moving at about 186,000 miles per second. Light is the fastest thing in the universe. Nothing can travel faster. It's not just a speed limit that we haven't broken yet. It's a fundamental law woven into the fabric of reality itself. And yet, even at this incomprehensible speed, to cross the observable universe from one side to the other, light would need 93 billion years. Think about that for a moment. If you somehow created a beam of light right now and aimed it across the observable universe, that light wouldn't reach the other side for 93 billion years. Humanity has existed for roughly 300,000 years. The dinosaurs went extinct 66 million years ago. The Earth formed about 4.5 billion years ago. That beam of light would still be traveling long after our sun burns out. Long after the Milky Way merges with Andromeda. Long after events we cannot even begin to predict. But wait, here's where things get genuinely strange. The universe is only about 13.8 billion years old. How can the observable universe be 93 billion light years across if the universe has only existed for 13.8 billion years? If light is the fastest thing in existence and the universe is only 13.8 billion years old, shouldn't the observable universe be at most 27.6 billion light years across? After all, light could only have traveled 13.8 billion light years in one direction since the beginning of time. The answer lies in the expansion of space itself. And this is where your intuition starts to completely fail you. When we say the universe is expanding, we don't mean that galaxies are flying apart through space like shrapnel from an explosion. That's the common misconception. We mean the space itself is stretching. The actual fabric of reality is expanding, carrying galaxies along with it like raisins in rising bread dough. Think of it like dots drawn on a balloon. As you inflate the balloon, the dots move apart from each other. But they're not moving through the rubber. The rubber itself is stretching, increasing the distance between them without any of the dots actually traveling anywhere. This is profoundly different from ordinary motion. When you drive your car down the highway, you're moving through space. The space itself stays put while you travel across it. But when the universe expands, space itself is stretching. Every point is moving away from every other point. Not because objects are traveling through space, but because there's more space appearing between everything. This expansion has been happening since the very beginning of time. Light from distant regions of the universe has been traveling toward us for billions of years. But while that light was traveling, the space between us and those regions was expanding. The light was crossing space even as more space was being created. By the time the light finally arrives at our telescopes, the region it originally came from has moved much farther away than the light has actually traveled. Let me make this more concrete. Imagine a galaxy whose light has been traveling toward us for 13 billion years. You might think that galaxy is 13 billion light years away, but it's not. During those 13 billion years, space has been expanding continuously. That galaxy is now about 46 billion light years away, because space has been stretching the entire time that light was in transit. The light took 13 billion years to reach us, but the starting point kept moving further away the whole time. Multiply that by 2 to account for both directions, both edges of the observable universe, and you get a cosmos about 93 billion light years across. This is how we can see things that are now 46 billion light years away in a universe that's only 13.8 billion years old. The light isn't traveling faster than it should. Space itself has been playing tricks on our intuition. This creates what astronomers call the cosmic horizon. It's a boundary beyond which we cannot see, not because there's nothing there, but because light from those regions hasn't had time to reach us yet. The universe almost certainly extends far beyond this horizon. The physics and mathematics strongly suggest it does, but we have no way of observing what's out there directly. The light simply hasn't arrived yet, and in many cases, it never will. Think about what this really means for our understanding of reality. When you look at the night sky on a clear evening, you're not seeing the universe as it is right now. You're seeing the past. Every single point of light is a time machine showing you what existed when that light began its journey. The light from the moon took about 1.3 seconds to reach your eyes, so you're seeing the moon as it was about a second ago. That's trivial. The light from the sun took about 8 minutes and 20 seconds to travel across the gulf of space between us. When you watch a sunset, you're watching the sun as it was over 8 minutes ago. If the sun somehow vanished right now, we wouldn't know for over 8 minutes, because the last photons would still be traveling toward us. The light from the nearest star system, Alpha Centauri, took about 4.3 years to reach us. When you look at Alpha Centauri, you're seeing it as it was during the previous presidential administration. If something catastrophic happened there right now, we wouldn't know until the mid-2020s. The light from the Andromeda Galaxy, the nearest large galaxy to our Milky Way, took about 2.5 million years to cross the void between us. When you look at Andromeda through a telescope, or even with your naked eye on a dark night, you're seeing it as it was when early human ancestors were just beginning to walk upright on the African savanna. Homo erectus hadn't evolved yet. Stone tools were primitive, and the photons you're seeing right now had already been traveling for thousands of centuries. And the oldest light we can see, The cosmic microwave background radiation has been traveling for 13.8 billion years. It shows us the universe as it was just 380,000 years after the Big Bang, when the cosmos first became transparent to light. When you detect the cosmic microwave background, you're seeing the universe as an infant, before any stars had formed, before any galaxies existed, before anything we would recognize had come into being. But here's the crucial point that changes everything. There's a limit, a hard boundary. No matter how powerful our telescopes become, no matter what revolutionary technologies we develop, no matter how clever our detection methods grow, we will never see beyond the cosmic horizon. This isn't a technological limitation that better engineering might overcome. It's a fundamental property of the universe itself. The speed of light and the age of the cosmos combine to create an absolute barrier to observation. The cosmic horizon is receding from us, which sounds like good news at first. As time passes, light from more distant regions finally reaches us, and our observable universe grows slightly larger. Every moment, photons that have been traveling for billions of years finally complete their journey and enter our telescopes. We're constantly seeing further into the universe than we could the day before, but there's a devastating catch. The universe's expansion is accelerating. Distant regions of space are moving away from us faster and faster. Dark energy, the mysterious force driving this acceleration, is pushing everything apart at an ever-increasing rate. Eventually, some regions will be receding so fast that their light will never reach us. Not in a billion years, not in a trillion years, not ever. They will cross a threshold beyond which they are moving away faster than light can travel toward us. This means the observable universe will eventually start shrinking from our perspective. Galaxies that we can see today, galaxies we've photographed and studied and catalogued, will eventually disappear beyond our cosmic horizon. They'll be carried away by the expansion of space faster than their light can travel toward us. One by one, distant galaxies will wink out of existence from our point of view, not because they're being destroyed, but because the universe's expansion will finally outpace the speed of their light. Future astronomers, billions of years from now, will see a much emptier universe than we do. They'll look out at the cosmos and see only the local group of galaxies, everything else having been swept beyond the cosmic horizon. They might conclude that the universe is much smaller than it actually is. They might not even know there was ever anything beyond their observable limit. The evidence will simply be gone, carried away by the expansion of space. Let me try to put the scale of the observable universe in perspective, because the numbers are genuinely difficult for human minds to grasp. Within those 93 billion light years, astronomers estimate there are about 2 trillion galaxies. That's 2,000 billion separate galaxies. And remember, our own galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. Some galaxies are much smaller, containing only a few billion stars. Others are enormous, containing trillions. The variety is staggering. If we try to count all the stars in the observable universe, the total number is roughly 200 billion trillion. Let me write that out so you can appreciate it. That's 200 followed by 21 zeros, 200 sextillion. More stars than there are grains of sand on every beach on Earth. More stars than the number of seconds that have elapsed since the Big Bang. More stars than we could ever count, even if every human who ever lived spent every moment of their existence doing nothing but counting. Each of those stars might have planets. The Kepler Space Telescope showed us that planets are common, perhaps more common than stars in some sense. There might be more planets in the observable universe than there are stars. Trillions upon trillions of worlds, some rocky like Earth, some gaseous like Jupiter, some with conditions we can barely imagine. And yet, all of this represents only what we can see. Every galaxy we've ever observed through our most powerful telescopes. Every star we've ever catalogued in our databases. Every planet we've ever discovered orbiting distant suns. Every cosmic structure we've ever mapped. All of it represents only the observable universe, only the portion of reality that light has had time to reveal to us. It's like standing on a tiny island in the middle of a vast ocean and being able to see only to the horizon. You know the ocean extends beyond what you can see. The physics demands it, but you have no idea how far. The observable universe might be like a single drop of water in an ocean that stretches infinitely in all directions, or it might be most of what exists. The terrifying truth is that we genuinely don't know, and that uncertainty is what makes the question of what lies beyond so fascinating and so deeply humbling. Now, let's talk about what happens at the edge of the observable universe. What would you experience if you somehow traveled to the cosmic horizon itself? The answer might surprise you. Nothing special. The cosmic horizon isn't a physical barrier. It's not a wall you could touch, or a membrane you could penetrate, or a boundary you could cross, like entering a new country. It's simply the limit of how far light has traveled since the beginning of the universe. The horizon is defined by us, by our location, not by anything physically present at that distance. If you were magically transported to a galaxy at the very edge of our observable universe, you wouldn't notice anything unusual. You wouldn't feel like you were at the boundary of anything. You'd see stars and galaxies all around you, just like we do from Earth. Space would look the same, physics would work the same, the cosmic scenery would be familiar. But here's the mind-bending part. From that distant galaxy's perspective, they would have their own cosmic horizon, their own observable universe, centered on their location. And Earth, our home, would be at the very edge of their observable universe, just as they're at the edge of ours. From their point of view, we're the ones living at the mysterious boundary. There's nothing special about our location in the cosmos. Earth isn't at the center of anything. We're not in a privileged position. Every single point in the universe has its own observable universe centered on itself. These observable universes overlap like countless overlapping bubbles or circles drawn on a page. Your observable universe and my observable universe are essentially identical because we're in the same location. But an observer in a distant galaxy has a different observable universe, shifted by their position, seeing things we can never see while being unable to see things we take for granted. And here's where it gets truly strange. Beyond all these overlapping observable universes, beyond the furthest observable horizon from any point in the entire cosmos, there might be regions of space that no observer anywhere can see. Not because no one is looking, but because the light hasn't reached anyone yet. There might be galaxies that exist right now, in this very moment, that no conscious being in the entire universe has ever observed, or will ever observe. This brings us to a profound realization that should reshape how you think about reality. The universe we observe might be just a tiny bubble of visibility floating in something much, much larger. We're like creatures living at the bottom of a deep, dark ocean, able to see only a small volume of water illuminated by our own bioluminescence. Beyond the reach of our glow lies darkness. We have no idea how deep the ocean goes or how far it extends in any direction. We can only see our little sphere of light. The cosmic microwave background radiation gives us our earliest glimpse of the universe, and understanding it is crucial to grasping our observational limits. This radiation is the afterglow of the Big Bang itself, released when the universe was only 380,000 years old. It permeates all of space, coming at us from every direction, a faint whisper of microwaves that tells us what the early universe was like. Before that moment, 380,000 years after the Big Bang, the universe was so hot and dense that light couldn't travel freely. Photons were constantly scattered by the plasma that filled all of space. The universe was opaque, like being inside a thick fog where you can't see more than a few feet in any direction. Light was produced, but it couldn't go anywhere. It bounced around chaotically, unable to carry information across cosmic distances. But as the universe expanded and cooled, something remarkable happened. Electrons and protons, which had been flying around freely in the hot plasma, finally combined to form neutral hydrogen atoms. This event is called recombination. Once the electrons were bound into atoms, they could no longer scatter light. The universe became transparent. Light was finally free to travel. The cosmic microwave background is the light that was released at that moment, the first light that could travel freely through space. It's been traveling ever since for 13.8 billion years, and it's just now reaching our telescopes. When we detect this radiation, we're seeing the universe as it was when it was only 380,000 years old. We're seeing the earliest image possible using light. But the cosmic microwave background is also a wall of light beyond which we cannot see using electromagnetic radiation. We can see back to 380,000 years after the Big Bang, but not before. That earlier epoch, the first 380,000 years of cosmic history, is hidden from us, at least when it comes to light. Scientists are developing new ways to peer beyond this wall, to push our observational limits even further. Gravitational waves, ripples in space-time itself, predicted by Einstein and detected for the first time in 2015, could potentially carry information from even earlier epochs. Gravitational waves don't interact with matter the way light does. They would have traveled freely, even through the opaque early universe. If we can detect primordial gravitational waves from the first moments after the Big Bang, we might glimpse events that happened in the first fraction of a second, long before the cosmic microwave background was released. Neutrinos offer another window. These ghostly particles barely interact with matter. Trillions of neutrinos pass through your body every second, and you never notice because they almost never hit anything. Neutrinos were released even earlier than the cosmic microwave background, when the universe was only about 1 second old. If we could detect these primordial neutrinos, we'd see even further back in time. But even these new windows have limits that cannot be transcended. There's a fundamental barrier called the Planck epoch, the first 10 to the minus 43 seconds after the Big Bang. That's a decimal point followed by 42 zeros and then a 1, an inconceivably small fraction of a second. Before this moment, the universe was so extreme, so hot, so dense, so fundamentally strange that our current physics simply breaks down. We don't have the theoretical tools to describe what happened during the Planck epoch. Quantum mechanics, which describes the behavior of particles at small scales, and general relativity, which describes gravity and the structure of space-time, contradict each other at these extreme conditions. Both theories work beautifully in their own domains, but at the Planck scale, they give incompatible answers. We need a theory of quantum gravity, a theory that unifies these two pillars of physics to understand what happened in those first instants. And despite decades of effort by the most brilliant physicists on Earth, we don't have such a theory yet. So the cosmic horizon isn't just about distance, it's also about time. There are events in the early universe that might be fundamentally unknowable, hidden not just by the expansion of space, but by the limits of physics itself. Even if we could somehow bypass the cosmic horizon, even if we could see to arbitrary distances, we might still be unable to understand what happened in those first moments. Let's consider what the observable universe actually contains. We've mapped billions of galaxies using surveys that scan the sky systematically. We've discovered thousands of exoplanets orbiting distant stars, some of them potentially habitable. We've detected gravitational waves from colliding black holes and merging neutron stars, opening an entirely new window on the cosmos. We've observed the birth of stars in massive molecular clouds and the death of stars in supernova explosions. We've measured the cosmic microwave background with extraordinary precision, finding patterns that tell us about the earliest moments of cosmic history. And in all of this, we found patterns that constrain what the universe beyond might look like. The universe is remarkably uniform on large scales. This is one of the most striking features of cosmology. No matter which direction you look, you see roughly the same density of galaxies, the same distribution of cosmic structures, the same types of objects arranged in similar patterns. But beneath this uniformity lies a deeper structure. When astronomers map the positions of millions of galaxies, they find something extraordinary. Galaxies aren't scattered randomly through space. They're arranged in a vast cosmic web, a network of filaments and walls surrounding enormous empty voids. The filaments are rivers of galaxies, stretching for hundreds of millions of light years. The walls are sheets of galaxies, thin and vast like cosmic membranes. And the voids are bubbles of almost perfect emptiness, regions where few galaxies exist, some spanning hundreds of millions of light years across. This cosmic web is the largest pattern in nature. It's the skeleton of the universe, the scaffolding on which everything hangs. And remarkably, we can see it repeating in every direction we look. The same web, the same filaments, the same voids. The pattern continues to the very edge of our observable universe, and presumably far beyond. Even more remarkably, this visible structure is just the tip of the iceberg. The galaxies we see trace an invisible scaffolding of dark matter, a mysterious substance that outweighs ordinary matter 5-1. Dark matter doesn't emit light. It doesn't interact with electromagnetism at all. We can only detect it through its gravitational influence. But without it, the cosmic web wouldn't exist. Galaxies wouldn't have formed. We wouldn't be here to wonder about any of this. This uniformity is called the cosmological principle. It's the idea that the universe looks essentially the same from every location on large enough scales. There's no center. There's no edge in any observable sense. There's no special direction. The universe is homogeneous, meaning every place is similar to every other place on large scales. The universe is isotropic, meaning every direction is similar to every other direction. This uniformity extends to the very edge of the observable universe. The cosmic microwave background is incredibly smooth. When we measure its temperature across the sky, we find variations of only about 1 part in 100,000. The universe at that early epoch was almost perfectly uniform, with only tiny fluctuations that would eventually grow into the galaxies and galaxy clusters we see today. But here's a deep puzzle that plagued cosmologists for decades. How did regions on opposite sides of the observable universe become so similar? Think about it. The cosmic microwave background comes to us from every direction. Light from one side of the sky has been traveling for 13.8 billion years from one direction. Light from the opposite side has been traveling for the same amount of time from the opposite direction. These two regions are separated by about 93 billion light years. Here's the problem. Light from one side hasn't had time to reach the other side. These regions have never been in causal contact. They've never exchanged any information. No signal, no influence, no interaction has ever connected them. And yet they have almost identical temperatures, identical properties, identical statistical features. How can regions that have never communicated be so precisely similar? If I heated 2 pots of water in different rooms and never let them interact in any way, you wouldn't expect them to reach exactly the same temperature. You'd expect random variations. Yet across the observable universe, separated by distances that light itself hasn't crossed, we see almost perfect uniformity. This is called the horizon problem. It's one of the deepest mysteries in cosmology. The uniformity we observe seems to require communication across distances that no signal could have traveled. Either there's some unknown mechanism that enforces uniformity without communication, or something very strange happened in the early universe. This puzzle is one of the main reasons scientists developed the theory of cosmic inflation, which we'll explore in the next part. Inflation offers an elegant solution to the horizon problem. But before we get there, let's sit with the observable universe for a moment longer. Let's appreciate what it represents and what its existence means for our understanding of reality. Everything you've ever known exists within this sphere of visibility. Every person who has ever lived, from the first humans in Africa to the astronauts who walked on the moon. Every civilization that has ever risen and fallen, from ancient Mesopotamia to modern nations. Every star that has ever been born in collapsing gas clouds or died in spectacular explosions. Every atom that makes up your body, forged in the hearts of stars billions of years ago. All of it exists within the observable universe. Every book ever written, every song ever sung, every love ever felt, every war ever fought, every discovery ever made, every thought ever thought, all of human experience, all of terrestrial history, all of cosmic evolution that we know about, fits within this sphere 93 billion light years across. And that observable universe, vast beyond comprehension, might be an infinitesimally small fraction of what actually exists. The cosmic horizon is not the edge of reality, it's the edge of our knowledge. Beyond it lies the unknown, and that unknown might be larger than anything we can imagine. For most of human history, we didn't even know there was a beyond. We thought the stars were fixed lighters on the celestial sphere just past the moon and planets. We thought the Milky Way was the entire universe, a single island of stars in infinite darkness. When we discovered that there were other galaxies, we thought the observable universe was everything, that we could see all there was to see. Each discovery has pushed the boundaries of the unknown further out. We discovered other galaxies, revealing that the Milky Way was just one among billions. We discovered the expansion of the universe, showing that space itself was dynamic and changing. we discovered the cosmic microwave background, giving us a window into the earliest visible moments of cosmic history. Each discovery revealed that reality was vaster than we had imagined. And now we've reached a limit that might be final. The cosmic horizon is not something we can push past with better telescopes, more sensitive detectors, or revolutionary new technologies. It's a fundamental boundary imposed by the speed of light and the age of the universe. To understand what lies beyond, we need to turn away from observation entirely. We need to turn to theory, to mathematics, to the equations that describe how the universe works. And those equations suggest something extraordinary. They suggest that the observable universe might be just a tiny fraction of a much larger cosmos. A cosmos so vast that our entire observable universe, with its 2 trillion galaxies and 200 sextillion stars, is essentially nothing compared to the whole. Less than a speck of dust in a hurricane. Less than an atom in the earth. Less than anything we have words to describe. The observable universe is real, it's measurable, it's the foundation of everything we know about cosmology. We can photograph it, study it, analyze it, and build theories about it. But it's also a prison of light and time that keeps us from seeing the full extent of reality. We are trapped within our cosmic horizon, able to look out but never to see beyond. What lies beyond that prison? What exists in the regions of space that light will never reveal to us? What structures, what phenomena, what realities might exist in the cosmic darkness beyond our view? To begin answering that question, we need to understand how the universe began. We need to understand the extraordinary event that might have stretched the cosmos to sizes beyond imagination. We need to understand inflation. In the previous section, we explored the observable universe and its cosmic horizon. We saw how the expansion of space creates a fundamental limit on what we can observe. We discovered that even at the speed of light, we can only see so far. The cosmic horizon imprisons our view, limiting us to a sphere 93 billion light years across. But we also encountered a deep puzzle. How did distant regions of the universe become so remarkably similar when they've never been in contact? How can opposite ends of the sky share identical properties when no signal has ever passed between them? The answer, according to modern cosmology, is inflation. And understanding inflation is absolutely crucial to understanding what might lie beyond the observable universe. Because inflation doesn't just explain the uniformity we observe. It tells us something profound about the true size of the cosmos. And that size is almost impossible to comprehend. Inflation is a theory about what happened in the first fraction of a second after the Big Bang. Not the first second, not the first millisecond, not even the first billionth of a second. We're talking about an almost inconceivably tiny sliver of time, a period that lasted perhaps from 10 to the minus 36 seconds to 10 to the minus 32 seconds after the beginning of time. Let me try to give you a sense of how short this period was. A second is something you can feel. You can count seconds. A millisecond is a thousandth of a second. Still somewhat graspable. A microsecond is a millionth of a second. A nanosecond is a billionth. These are durations that high-speed cameras can capture, that computers operate on. But 10 to the minus 36 seconds? That's a decimal point followed by 35 zeros and then a 1. It's so brief that if you scaled it up so that it lasted 1 second, a single actual second would last longer than the current age of the universe, multiplied by itself trillions upon trillions of times. During this unimaginably brief instant, something extraordinary happened. Space expanded faster than light. As we explored earlier, this doesn't violate Einstein's laws because relativity only limits how fast things travel through space. Space itself has no speed limit. And during inflation, space exploited that freedom to the most extreme degree imaginable. During the inflationary period, the universe doubled in size roughly every 10 to the minus 37 seconds. That might not sound impressive at first. Doubling something seems mundane. You double a number and you get twice the original. What's the big deal? The big deal is how many doublings occurred in that brief window of time. The universe didn't just double once. It doubled over and over and over again in incredibly rapid succession. Estimates suggest the universe underwent at least 60 doublings during inflation. Some models predict even more, 70 doublings, 80, perhaps hundreds. To understand how powerful exponential growth truly is, consider this thought experiment. If you start with 1 and double it 60 times, you get a number larger than 1 quintillion. That's a 1 followed by 18 zeros. 1 quintillion is larger than the number of grains of sand on Earth. It's larger than the number of drops of water in all the world's oceans. But inflation was much more extreme than doubling a single number. The entire universe doubled 60 times or more. Every dimension, every direction, the whole fabric of space, a region smaller than a proton, smaller than any particle we've ever detected, smaller than anything we can meaningfully describe, expanded to become larger than the entire observable universe today. And all of this happened in less than a trillionth of a trillionth of a trillionth of a second. This solves the horizon problem that we encountered in the previous section. Remember, the puzzle was that regions on opposite sides of the observable universe have identical properties, despite never having been in contact. No signal could have traveled between them in the age of the universe. How could they be so similar? Inflation provides an elegant answer. Before inflation, the entire observable universe, and much more beyond it, was contained in a region so small that light had plenty of time to cross it. Everything was in contact. Every part of that tiny primordial patch could communicate with every other part. They could exchange energy. They could reach thermal equilibrium. They could become identical because they were all connected, all interacting, all influencing each other. Then inflation struck. That tiny uniform region was stretched to cosmic scales. The uniformity that existed at microscopic sizes was blown up to span billions of light years. The identical properties we observe across the sky aren't a mystery requiring communication across vast distances. They're a relic of an earlier time when those regions were close enough to touch. The uniformity we observe today is the echo of that early contact, stretched across the sky by the most violent expansion in cosmic history. The cosmic microwave background smoothness, that 1 part in 100,000 uniformity that puzzled cosmologists for decades, is inflation's fingerprint on the universe. But here's what's truly crucial for our question about what lies beyond the observable universe. Inflation didn't just expand our little patch of cosmos, it expanded everything. And this is where the implications become almost impossible to absorb. If inflation happened as the theory describes, then the actual universe is vastly, almost incomprehensibly larger than the observable universe. The 93 billion light years we can see is not most of the universe. It's not even a significant fraction. It might be less than an atom compared to an ocean, less than a single electron compared to the entire observable cosmos. How much larger? This is where the numbers become almost meaningless. where mathematics fails to convey any intuitive understanding. Some calculations suggest the actual universe is at least 10 to the 23 times larger than the observable universe. That's a 1 followed by 23 zeros. Let me try to put that in perspective with an analogy. If the observable universe, with its 93 billion light years and 2 trillion galaxies, were shrunk down to the size of a single atom, the actual universe would be larger than the observable universe at its normal scale. Read that again. The observable universe as an atom. The actual universe larger than the observable universe. That's how much inflation expanded the cosmos. But other calculations are even more extreme. Depending on exactly how inflation occurred, how strong the inflaton field was, and how long the inflationary period lasted, the actual universe might be 10 to the 10 to the 123 times larger than what we can observe. That's not a typo. That's a number raised to a power raised to another power. It's a number so large that writing it out in full, digit by digit, would require more digits than there are atoms in the observable universe. We literally cannot write down how large the universe might be. Let me try one more approach to make this concrete. The observable universe is 93 billion light years across. It contains roughly 2 trillion galaxies. Each of those galaxies contains hundreds of billions of stars. The total number of stars we can see is around 200 billion trillion. That's already an incomprehensible number. But if the actual universe is 10 to the 23 times larger than what we observe, it would contain roughly 10 to the 23 times more galaxies. Let me try to express that. It would be approximately 10 trillion galaxies. That's not poetic exaggeration. That's a mathematical estimate. And it might be far too conservative. And here's something even stranger. The universe might be infinite. Inflation could have expanded a finite region to infinite size. Mathematics allows for this. Under certain conditions, exponential growth can carry a finite quantity to infinity in finite time. Alternatively, the pre-inflationary universe might have already been infinite, and inflation simply expanded an already infinite universe to an even larger infinity. You might think infinity is infinity. How can there be larger infinities? But mathematicians have proven that there are indeed different sizes of infinity. Some infinities are countable, like the set of all whole numbers. Others are uncountable, like the set of all real numbers. There are infinitely many whole numbers, but there are more real numbers than whole numbers, even though both sets are infinite. The inflationary universe might be the largest kind of infinity, an infinity so vast that smaller infinities are negligible in comparison. But why should we believe inflation actually happened? It's an extraordinary claim. The universe expanded faster than light in the first trillionth of a trillionth of a trillionth of a second. What evidence supports such a radical idea? The first piece of evidence is the horizon problem itself. Without inflation, there's simply no good explanation for why the cosmic microwave background is so uniform. How do regions that have never communicated share identical temperatures to 1 part in 100,000? Inflation provides the only satisfying answer. They were in contact before inflation, then stretched apart. The second piece of evidence is something called the flatness problem. General relativity, Einstein's theory of gravity, tells us that the geometry of space depends on its energy density. If the density is above a certain critical value, space curves positively, like the surface of a sphere. parallel lines eventually converge. Triangles have angles that add up to more than 180 degrees. If the density is below the critical value, space curves negatively, like a saddle. Parallel lines diverge. Triangles have angles that add up to less than 180 degrees. And if the density is exactly at the critical value, space is flat, like a sheet of paper. Parallel lines stay parallel forever. Triangles have angles that add up to exactly 180 degrees. Observations show that the universe is flat to remarkable precision. Less than 0.5% deviation from perfect flatness. Our universe is, for all practical purposes, geometrically flat. But here's the puzzle. The flatness of the universe is unstable. Even tiny deviations from flatness in the early universe would have grown enormously over time. If the early universe had been just slightly more curved than flat, that curvature would have amplified over billions of years. By now, the universe would be obviously curved, dramatically different from what we observe. For the universe to be as flat as we measure today, it must have been incredibly close to flat at the beginning. Unnaturally close. The deviation from flatness must have been less than 1 part in 10 to the 60. That's like balancing a pencil on its tip so perfectly that it doesn't fall over for billions of years. It requires such fine-tuning that it seems absurd unless there's a mechanism that enforces flatness. Inflation provides that mechanism. Inflation acts like a cosmic smoothing machine. It stretches space so dramatically that any initial curvature is diluted to nothing. Imagine drawing a small curved line on a balloon. The curve is obvious when the balloon is small. But now inflate the balloon to the size of the Earth. That same curve would appear perfectly straight because the expansion stretched it to such an enormous scale. Any visible curvature disappears when you zoom in enough. Inflation does the same to the curvature of space. It stretches the universe so much that any initial curve becomes indistinguishable from flat. The third piece of evidence is perhaps the most remarkable. Inflation explains the origin of cosmic structure itself. The galaxies and galaxy clusters we see today grew from tiny variations in the density of the early universe. Some regions were slightly denser than average, attracting more matter through gravity, eventually collapsing into galaxies. Other regions were slightly less dense, becoming the voids that separate galaxy clusters. But where did those initial density variations come from? Why wasn't the early universe perfectly smooth? Inflation provides an answer that sounds like science fiction, but is actually mainstream physics. During inflation, quantum fluctuations occurred in the fabric of space itself. Quantum mechanics tells us that on the smallest scales, nothing is ever perfectly still or perfectly smooth. Even empty space seethes with tiny fluctuations, particles popping in and out of existence, fields vibrating randomly. These quantum effects are usually confined to the subatomic realm, invisible at the scales of everyday life, but inflation stretched them to cosmic sizes. A quantum fluctuation smaller than an atom, a random jitter in the fabric of space-time, was blown up to become a region larger than a galaxy cluster. These stretched fluctuations became the seeds of cosmic structure. The pattern of galaxies across the sky, the web of filaments and voids that make up the cosmic structure, ultimately traces back to quantum randomness in the first fraction of a second. This is perhaps the most profound prediction of inflation. It says that the largest structures in the universe, galaxy clusters and superclusters spanning hundreds of millions of light years, grew from quantum effects that occurred in the first instant of time. The quantum and the cosmic are linked. The smallest scale phenomena in physics determine the largest scale structures in the universe. The cosmic microwave background preserves a snapshot of these primordial fluctuations. The tiny temperature variations we measure, that 1 part in 100,000 pattern, correspond exactly to what inflation predicts. These statistical properties of the fluctuations, their distribution across different angular scales, their correlations and patterns, all match the inflationary model with extraordinary precision. This is not vague agreement. This is precise quantitative confirmation across multiple independent measurements. There's another piece of evidence that scientists are actively searching for. Inflation should have produced primordial gravitational waves, ripples in space-time itself generated by the violent expansion. These gravitational waves would have left a distinctive pattern in the cosmic microwave background, a swirling signature called B-mode polarization. Detecting this pattern would be a smoking gun for inflation. It would tell us not just that inflation happened, but how energetic it was, how rapidly space expanded, what the inflaton field was like. It would open a window into the first trillionth of a trillionth of a trillionth of a second, an epoch we can probe in no other way. Several experiments are searching for this signal right now, scanning the microwave sky with extraordinary precision. So far, the primordial B modes haven't been definitively detected, but the search continues. If found, they would transform our understanding of the early universe and provide powerful support for the inflationary paradigm. So, inflation is well supported by evidence. It's not a fringe theory. It's not speculation. It's a central pillar of modern cosmology, endorsed by the vast majority of working cosmologists, supported by decades of observations. And if inflation is correct, then the universe beyond our cosmic horizon is not just slightly larger than what we can observe. It's vastly, incomprehensibly, almost infinitely larger. But inflation raises as many questions as it answers. If the universe is so much larger than what we can see, what's actually out there? Is it just more of the same? More galaxies, more stars, more planets, stretching on and on forever? Or is there something different? Something stranger? Here's where things get speculative but genuinely fascinating. If inflation happened once, it might not have been a one-time event. Many physicists believe inflation is eternal. Once it starts, it might never completely stop. The inflaton field doesn't decay everywhere at once. Some regions stop inflating and become pocket universes like ours, but other regions keep inflating. And because inflation expands space so rapidly, the inflating regions always dominate. Inflation perpetuates itself, spawning pocket universes forever. In this picture, our observable universe is one bubble in an infinitely expanding foam. We're inside a pocket where inflation ended about 13.8 billion years ago. But beyond our cosmic horizon, far beyond the 93 billion light years we can see, more pockets are forming. Other bubbles, other universes. This is the multiverse, not science fiction, but a direct consequence of our best theories about how the universe began. If inflation happened, and evidence strongly suggests it did, then the multiverse might be real, but let me be clear about the limitations. The multiverse is not proven. It's a prediction of some inflationary models, but not all. Some versions of inflation are eternal, naturally generating infinite pocket universes. Other versions are not, producing a very large but potentially finite cosmos without separate bubbles. We don't know which version correctly describes our universe, and even if eternal inflation is correct, We might never be able to prove it directly. The other pocket universes are beyond our cosmic horizon, forever causally disconnected from us. We can't observe them. We can't detect them. We can't send signals to them or receive signals from them. They are, in principle, unobservable. The best we can do is look for indirect evidence. Patterns in the cosmic microwave background that might indicate a collision between our bubble and another. Statistical anomalies that might support eternal inflation over alternative models. Theoretical arguments about which inflationary models are most natural or most consistent with other physics. Some physicists argue that the multiverse is not even science. Science requires testable predictions, they say. If we can never observe other universes, how can we test the theory? This is a legitimate concern, and it's the subject of intense, ongoing debate in the physics community. But here's another perspective worth considering. Just because something is unobservable doesn't mean it doesn't exist. We can't directly observe the interior of black holes, but we're confident black holes exist based on their external effects. We can't directly observe quarks, but we're confident they exist based on the behavior of particles that contain them. The multiverse might be similar. We might find indirect evidence that strongly supports its existence, even if we can never observe it directly. Let's step back and consider what inflation tells us about what lies beyond the observable universe, separating what's fairly certain from what's speculative. At minimum, inflation suggests the universe is vastly larger than what we can see. Even without eternal inflation, even without the multiverse, the expansion during the inflationary epoch would have created a cosmos far exceeding our cosmic horizon. This extended universe would presumably contain more of what we observe. More galaxies, more stars, more planets. The laws of physics would be the same. The conditions would be similar. It would just be more universe, stretching on and on, far beyond anything we can observe. If eternal inflation is correct, then beyond our cosmic horizon lies not just more of the same universe, but infinitely more universe, structured in a different way. An endless expanse of inflating space, constantly spawning new pocket universes, each with its own Big Bang, its own cosmic history, its own evolution from hot plasma to galaxies to whatever comes next. Some of these pocket universes might be nearly identical to ours. The same physical constants, the same particles, the same forces. A physicist transported from our universe to one of these similar pockets might not even notice the difference. The laws would be familiar, the phenomena would be recognizable, but other pocket universes might be radically different. When the inflaton field decays, it might decay in different ways, producing different conditions. The physical constants that govern our universe, things like the strength of gravity, the mass of the electron, the speed of light, these might have different values in other pockets. The particles that exist might be different. The forces that hold matter together might work differently. Some of these different universes might be sterile, unable to support complex structures. If the nuclear force was slightly weaker, atoms heavier than hydrogen couldn't form. No carbon, no oxygen, no life as we know it. If gravity was slightly stronger, stars would burn out quickly, not giving life time to evolve. Most random combinations of physical constants probably don't permit anything interesting to happen. But others might support complexity in ways we can't imagine. Different particles organizing in different ways. Different chemistry based on different atomic structures. Different forms of matter, different sources of energy. Different possibilities for evolution and complexity. We can barely imagine what such universes would be like, but mathematics suggests they're possible. And if you go far enough beyond even the multiverse, you reach realms that might not even be describable by physics as we understand it. Regions of eternally inflating space that have never decayed, never formed matter, never had anything we would recognize as a Big Bang. Pure inflation, pure expansion, stretching on forever, devoid of particles or structures or time as we understand it. This is what our best theories suggest lies beyond the observable universe. Not nothing, not empty void, not the edge of reality, but more cosmos than we can possibly imagine. An ocean of existence in which our observable universe, with all its trillions of galaxies and sextillions of stars, is less than a single atom. Perhaps infinitely less. The inflation that created everything didn't just create what we can see, it created vastly, incomprehensibly more. It created a cosmos that extends beyond our cosmic horizon, beyond eternal inflation's pocket universes, beyond perhaps even the reach of any description we can formulate. And understanding that creation, even partially, even speculatively, helps us grasp the scale of what we cannot see. The observable universe is not the universe. It's a window. A tiny window in a house of infinite rooms. And inflation is what built that house, expanding a quantum fluctuation into everything that exists or might exist. But inflation is just the beginning of our exploration. In the next section, we'll delve deeper into the theories of what might actually exist in those unreachable realms. We'll explore the multiverse in more detail. We'll encounter the strange possibility of different physical laws. We'll confront string theory and its landscape of possibilities. And we'll wrestle with the strangest question of all. What if there is no edge? What if existence truly extends forever, in every direction, in every possible form? We've established that the observable universe is just a tiny fraction of what exists. Inflation expanded the cosmos to scales far beyond our cosmic horizon, stretching a region smaller than a proton into something vastly larger than everything we can see. The numbers are almost meaningless in their enormity, 10 to the 23 times larger than the observable universe, perhaps infinitely larger, perhaps containing more variations of reality than we can possibly imagine. But now we need to confront a deeper and more unsettling question. What actually exists out there? Beyond the cosmic horizon, beyond the reach of any telescope we could ever build, beyond the light that will ever reach us, what is there? Is it just more of the same? More galaxies spinning through the void, more stars burning hydrogen, more planets orbiting in the darkness? Or is it something stranger? Something fundamentally different? Something our minds might struggle to comprehend? Let's explore the theories. Because physicists have spent decades thinking about this question, and their answers range from the conservative to the genuinely mind-bending. The simplest possibility is that the universe beyond our cosmic horizon is just more universe. Same physics, same types of galaxies, same cosmic structure, same laws governing everything. You could travel for trillions upon trillions of light years, far beyond anything we can observe, and you would see essentially the same thing. Stars being born in collapsing clouds of gas, galaxies spinning in their slow gravitational dance, black holes consuming matter at the centers of galaxies, the cosmic web of filaments and voids extending in every direction, the same pattern repeating on the largest scales. In this picture, there's nothing special about our location. We're not at the center of anything. We're not in a privileged position. We're just somewhere, One random point in an incomprehensibly vast cosmos, and every somewhere looks pretty much like every other somewhere when you zoom out far enough. This is actually the most scientifically conservative view. It requires no new physics, no exotic concepts, no radical departures from what we already understand. It's just the straightforward extension of what we observe. The laws of physics don't change as you move through space. The universe is homogeneous, meaning every place is similar to every other place on large scales. The universe is isotropic, meaning every direction is similar to every other direction. What's out there is simply what's here, extended without limit. If this conservative view is correct, then the universe beyond our cosmic horizon contains unimaginable numbers of galaxies, stars, and planets. Given the uniformity we observe within the observable universe, we can extrapolate outward with some confidence. If the actual universe is 10 to the 23 times larger than the observable universe, it contains roughly 10 to the 23 times more of everything. More galaxies than there are atoms in your body. More stars than there are grains of sand on every beach on every planet we could ever visit. More planets than we could count if we counted for the entire remaining lifetime of the universe. But this apparently simple picture raises a genuinely strange consequence that most people don't consider. If the universe is large enough, anything that can happen will happen. Not just once, not just occasionally, but infinitely many times. Here's the reasoning, and it's mathematically rigorous, even if it sounds like fantasy. The observable universe is finite. It contains a finite number of particles arranged in a finite number of possible configurations. There are only so many ways to arrange roughly 10 to the 80 particles, which is approximately the number of particles in the observable universe. That's an enormous number, vastly larger than anything in everyday experience, but it's still finite. There's a limit to the possible arrangements. Now, if the universe beyond our horizon is infinite, or even just vastly larger than the observable universe, then every possible arrangement of particles exists somewhere. Every possible configuration of matter, every possible planet, every possible life form, every possible civilization, every possible history. This means that somewhere out there, impossibly far away, far beyond any distance we can meaningfully describe, there's another Earth. Another solar system identical to ours. Another Milky Way galaxy with the same spiral arms. Another you. Sitting wherever you're sitting right now, reading or listening to these exact words at this exact moment. In fact, there aren't just one or two copies. There are infinitely many copies of Earth. Infinitely many copies of you. Infinitely many versions of this exact moment. Some of these copies are identical down to the quantum level. Every particle in exactly the same position. Every thought in your brain exactly mirrored. But others are slightly different. In some, you made a different choice yesterday. In some, a cosmic ray flipped a single bit in your DNA decades ago, leading to cascading differences. In some, history took a different path centuries ago. The variations extend in every direction, exploring every possibility that physics allows. This isn't mysticism dressed up in scientific language. This isn't wishful thinking about parallel lives. This is mathematics. Pure, cold, rigorous mathematics. If you have infinite space and finite configurations, every configuration must repeat. It's not a question of probability. It's a certainty. Your nearest, identical copy, an exact duplicate down to the atomic level, is estimated to be about 10 to the 29 meters away. That's a distance so incomprehensibly vast that calling it astronomical is laughable understatement. But in an infinite universe, that distance exists. That copy of you exists, and so do infinitely many others. This concept is sometimes called the level 1 multiverse. It's just one infinite universe with repeating patterns, but from your perspective, these distant regions are utterly unreachable, as separated from you as any parallel universe. Now, let's consider more exotic possibilities, because the level 1 multiverse, strange as it sounds, is actually the conservative option. Things get much stranger from here. We explored eternal inflation in the previous section, how the inflaton field decays in some regions while continuing to inflate in others, spawning an endless foam of pocket universes. But now let's consider what those pocket universes might actually contain and what other mechanisms might generate multiple realities. Here's what makes pocket universes potentially so strange. The laws of physics as we experience them might not be fundamental. They might be emergent, arising from deeper structures that can take multiple forms. When the inflaton field decays in a particular region, the exact manner of that decay might determine what particles exist, what forces operate, and what constants govern behavior in the resulting pocket universe. Think of it like water freezing into ice. Water can freeze into many different crystal structures depending on the conditions. The same H2O molecules can arrange themselves in different patterns, creating different types of ice with different properties. Similarly, the underlying quantum fields of the universe might be able to crystallize into different configurations, each one a different set of physical laws. In our pocket universe, the inflaton field decayed in a particular way, producing electrons and quarks and photons, producing gravity and electromagnetism and the nuclear forces, producing the specific values of constants like the speed of light and Planck's constant. But in another pocket universe, the decay might have gone differently. Different particles, different forces, different constants, a completely different version of physics. Some of these alternative physics might be similar to ours. The electron might be slightly heavier, gravity might be slightly stronger. The differences might be subtle, perhaps even undetectable without precise measurements. Such universes might look much like ours, with stars and galaxies and perhaps even life, just with slightly different details. But other pocket universes might be radically different. They might have particles we've never imagined, forces that don't exist in our physics, structures that our mathematics can barely describe. They might be so alien that the very concepts of space, time, and matter don't apply in any recognizable way. This is the level 2 multiverse, not just infinite copies with the same physics, but separate domains with genuinely different rules. Each pocket universe is its own complete reality, with its own version of physics, its own possibilities, its own constraints on what can exist. We might be surrounded by universes where life is impossible, universes of eternal darkness where no star ever shines, universes of pure radiation where no matter ever forms, universes that collapsed into black holes before a single second passed, universes with physics so different that the very concepts of space, time, and matter don't apply in any way we would recognize. And between these pocket universes, separating them forever, might be regions of eternally inflating space. These are barriers that can never be crossed, not because they're solid walls, but because they're expanding faster than anything could travel. Even light, even information, even the very concept of causality cannot bridge the gap. The pocket universes are truly separate, isolated islands of reality in an endless, churning sea of inflation. But eternal inflation isn't the only theoretical path to multiple universes. String theory, one of the leading candidates for a theory of quantum gravity, also suggests the existence of many universes through a completely different mechanism. String theory proposes that the fundamental constituents of reality are not point-like particles, but tiny vibrating strings. These strings are unimaginably small, about 10 to the minus 35 meters in length, far smaller than any particle we have ever detected, far smaller than any experiment could directly probe. Different vibration patterns of these strings correspond to different particles. One vibration pattern gives you an electron, another gives you a quark, another gives you a photon. All the particles we observe are, in this theory, just different notes played on the same fundamental strings. The theory is mathematically elegant, praised by physicists for its beauty and internal consistency, but it has a feature that some consider a problem. It doesn't predict one unique universe. It predicts an enormous number of possible universes. String theory requires extra dimensions beyond the 3 spatial dimensions we experience. Instead of just length, width, and height, string theory needs 6 or 7 additional spatial dimensions for its mathematics to work. These extra dimensions aren't obvious because they're curled up at tiny scales, compactified into shapes so small we can't detect them directly. But here's the crucial point. There are many different ways these extra dimensions can be curled up. Many different shapes. Many different configurations. Each configuration corresponds to a different set of physical laws in the resulting 3-dimensional universe. The particles that exist, the forces that operate, the constants that govern behavior, all depend on exactly how those extra dimensions are configured. The number of possible configurations in string theory is estimated at 10 to the 500. Let me try to convey how large that is. It's a 1 followed by 500 zeros. If you wrote 1 digit per second, writing out that number would take longer than the age of the universe. If every atom in the observable universe could store 1 configuration, you'd still fall short by hundreds of orders of magnitude. This vast collection of possibilities is called the string landscape. If string theory is correct, and if there's some mechanism to realize different points in the landscape, then there might be 10 to the 500 different kinds of universes, each with different physics. The overwhelming majority would probably be incompatible with life, with stable atoms, with anything we would recognize, but a tiny fraction of 10 to the 500 is still an astronomically large number. There might be countless universes capable of supporting complexity, just with different details than ours. This raises a profound question known as the fine-tuning problem. Why do the physical constants in our universe have the values they do? The strength of gravity, the mass of the electron, the energy of empty space, all of these could have been different. And if they were even slightly different, we wouldn't be here to ask the question. If gravity were slightly stronger, stars would burn too hot and die too quickly for life to evolve. If the strong nuclear force was slightly weaker, atoms heavier than hydrogen couldn't form. If the cosmological constant were much larger, the universe would have torn itself apart before galaxies could form. The constants seem finely tuned for life. Some see this as evidence of design, a universe crafted for conscious beings. But the multiverse offers another explanation. If countless universes exist with different constants, then of course we find ourselves in one compatible with life. We couldn't find ourselves anywhere else. This is the anthropic principle. It's not that the universe was designed for us, it's that we can only exist in universes that permit our existence. This doesn't mean every universe has observers. Most probably don't. But somewhere in the vast multiverse, by pure chance, constants align to permit complexity. And those rare universes, however improbable, are the only ones that can be observed from the inside. And then there's quantum mechanics. The strangest theory in all of physics, proven correct to more decimal places than any other theory in science, and perhaps the most suggestive of multiple realities. In quantum mechanics, particles don't have definite properties until they're measured. Before measurement, a particle exists in what's called a superposition, a combination of all possible states it could be in. An electron doesn't have a definite position until you look for it. It exists as a spread out wave of probability, potentially here, potentially there, potentially everywhere allowed by the equations. When you measure the particle, the superposition collapses. You get a definite result. The electron is here, not there. The probability wave becomes a concrete actuality. But what causes this collapse? What singles out one outcome from all the possibilities? This is the measurement problem, one of the deepest unsolved mysteries in physics, debated for nearly a century without resolution. One proposed solution is radical. There is no collapse. Nothing singles out one outcome. All outcomes happen. The universe splits. This is the many worlds interpretation of quantum mechanics, proposed by physicist Hugh Everett in 1957. Every time a quantum event has multiple possible outcomes, the universe branches. All outcomes occur, but in different branches. The branches diverge and never interact again. From inside each branch, only one outcome appears to have happened. But all outcomes are equally real, equally actual, equally existing. If many worlds is correct, the implications are staggering. The multiverse isn't just out there in distant space, separated from us by billions of light years. It's here, right here, branching off from this very moment, this very second, this very quantum event occurring in your brain right now. Every quantum decision and quantum decisions are happening constantly. Trillions upon trillions per second in every atom of your body creates new universes. The multiverse isn't something you would travel to. It's something that proliferates around you constantly, like an ever-branching tree growing new limbs at incomprehensible speed. In the many worlds multiverse, there are branches where you turned left instead of right this morning. Branches where you said something different in a conversation yesterday. Branches where a cosmic ray struck differently and triggered a cascade of changes. Branches where history diverged centuries ago. Every possibility permitted by quantum mechanics exists in some branch somewhere. Now, let me be very clear about something important. All of these multiverse theories are speculative. None have been proven, none have been directly observed, and by their nature, many might be unobservable in principle. Some physicists embrace these ideas as the natural consequences of our best theories. Others reject them as unfalsifiable speculation that has crossed the line from physics into philosophy, or even metaphysics. But here's what's remarkable, regardless of where you stand on these debates. These theories arise naturally from our best attempts to understand fundamental physics. They're not invented out of thin air to explain away mysteries or satisfy philosophical preferences. They emerge from the mathematics itself. Inflation leads naturally to eternal inflation under many conditions. String theory leads naturally to the landscape as a consequence of its structure. Quantum mechanics leads naturally to many worlds as one. Resolution of the measurement problem. What about the possibility that there's nothing beyond the observable universe? What if the universe is finite and simply ends at some boundary? This is theoretically possible, but it raises immediate problems. If the universe has an edge, what's beyond the edge? If you traveled to the boundary and somehow reached it, what would you find? A wall of some kind? Empty space extending further? Something that isn't space at all? The very concept of nothing, of a true absence, is philosophically treacherous. Our minds naturally ask what's on the other side of any boundary. The question seems to demand an answer even when there might not be one. One elegant way around this problem is if the universe is finite but unbounded. These two words seem contradictory in ordinary language, but geometry allows for such things. Consider the surface of a sphere. It's finite in area. You could calculate exactly how many square meters it contains, but it has no boundary. If you walk in any direction on a sphere, you never reach an edge. You eventually return to where you started, having circumnavigated the surface without ever encountering a border. The universe might be like this in higher dimensions. Space itself might curve back on itself. If you traveled far enough in one direction, you would eventually return to where you started. The universe would be finite in volume, containing a specific, measurable amount of space, but it would have no edge, no boundary, no wall you could reach and wonder what's beyond. Current observations suggest the universe is flat, not curved in this way. Our measurements of the cosmic microwave background, of the distribution of galaxies, of the geometry of cosmic structures, all indicate that space is flat to remarkable precision. But flat could mean nearly flat. A sphere large enough appears flat locally. The surface of the Earth seems flat when you're standing on it because the curvature is so gradual. The universe might be curved on scales vastly larger than the observable universe, appearing perfectly flat to us because we can only see an infinitesimally small portion. Here's perhaps the strangest possibility we've yet considered. What if beyond the universe lies not more space at all, but something else entirely? What if our universe is embedded in a higher dimensional reality? What if reality is far more complex than 3 dimensions of space and 1 of time? String theory, as I mentioned, requires extra dimensions. In some versions, these extra dimensions are curled up at scales too small to detect, but other versions propose large extra dimensions. Dimensions that extend as far as our familiar 3, but are somehow inaccessible to us. In the brain world scenario, our universe is a 3-dimensional membrane, a brain floating in a higher dimensional space called the bulk. Think of it like a sheet of paper floating in a room. The paper is 2-dimensional, a surface. The room is 3-dimensional, a volume. Creatures confined to the paper could move in 2 directions but never up or down into the room. They would be unaware of the room's existence, unable to perceive the dimension perpendicular to their surface. Similarly, we might be confined to our 3-dimensional brain, unable to perceive or access the higher dimensional bulk in which it floats. Other brains might exist in the same bulk. Parallel universes just a tiny distance away in the extra dimension, perhaps only millimeters away, but completely inaccessible because we can't move in that direction. We can't see these other brains because light is confined to our brain. Photons travel along the membrane, unable to leap across the bulk to another surface. We can't touch these other universes because all our matter is stuck to our brain. Electrons, protons, everything we're made of is bound to our membrane. But gravity might be different. In some versions of brain cosmology, gravity can leak between brains. It's not confined the way light and matter are. The gravitational influence of a nearby brain might be detectable in our universe, perhaps explaining some of the mysterious dark matter or dark energy that we've detected, but can't identify. And what about the Big Bang itself? What came before it? What exists outside of time as we know it? The Big Bang is often described as the beginning of everything. Space, time, matter, energy, all created in a single moment roughly 13.8 billion years ago. Before the Big Bang, there was no before because time itself began with the Big Bang. The question of what came before is like asking what's north of the North Pole. It's a question that sounds meaningful but might not have an answer. But this picture is probably too simple. The Big Bang, as we usually imagine it, might be just a local event. The birth of our particular pocket universe in a larger, eternally inflating cosmos that has no beginning and no end. Before our Big Bang, there might have been eternal inflation stretching backward forever. There might have been other universes being born, other Big Bangs igniting in the endless foam. The Big Bang might not be the absolute beginning of existence, just the beginning of our particular cosmic history, our particular chapter in an endless book. And what about the ultimate question? What exists beyond all possible universes? Beyond the multiverse in all its forms? Beyond the bulk? Beyond the mathematical structures that might encode all possible realities? Here we reach the absolute limits of physics. We reach the realm where science shades into philosophy, where equations give way to pure speculation. Some thinkers propose that beyond all physical reality lies pure mathematics. Mathematical structures exist necessarily, timelessly, independently of any physical instantiation. They don't need a universe to contain them. They simply are. And perhaps all possible physical realities are just mathematical structures made manifest, patterns in the abstract realm of mathematics that happen to include conscious observers. Others suggest that beyond everything lies true nothing. Not empty space, which is still something. Not a vacuum, which in quantum mechanics seethes with activity. True nothing. The absence of anything. The absence of even the possibility of anything. But this nothing might be unstable. Perhaps nothing naturally fluctuates into something. Perhaps existence is more natural than non-existence. Perhaps the question of why there is something rather than nothing is answered simply. Nothing is impossible, and something is inevitable. What we can say is this. Physics suggests that beyond the observable universe lies vastly more cosmos, more galaxies, more stars, more planets, and possibly much more than that. Other universes with different physics. Eternal inflation spawning endless pocket cosmos. A string landscape with 10 to the 500 possibilities. Quantum branches proliferating constantly. Higher dimensions containing parallel brains. Perhaps mathematical structures encoding all possible realities. The observable universe is our prison. We will never see beyond it directly. No telescope will ever pierce the cosmic horizon. No signal will ever reach us from beyond. But reason and mathematics can take us further than direct observation. They suggest that what lies beyond is not nothing. It's everything. An infinity of realities, of possibilities, of existence extending without limit. And in that infinity, we're not central. We're not special. We're not privileged. We're just here, in this one pocket, in this one branch, on this one brain, looking out at the cosmic horizon and wondering what lies beyond. We've journeyed from the cosmic horizon to the inflationary expansion, from the multiverse to the very edges of physics itself. We've explored what the observable universe contains and confronted the staggering possibility that it represents only an infinitesimal fraction of what exists. We've encountered eternal inflation spawning endless pocket universes, the string landscape with its 10 to the 500 possible configurations of physics, quantum branches proliferating constantly, and higher dimensions that might contain parallel realities millimeters away, yet forever unreachable. Now we confront the deepest question of all. A question that isn't just about physics or cosmology, but about the nature of knowledge itself. Can we ever truly know what exists beyond the universe? Or are there fundamental limits to human understanding that can never be transcended, no matter how clever we become, no matter how advanced our technology grows, no matter how long our species survives? Let's begin with what we can know, because the story of human discovery is remarkable, and it gives us reason for both hope and humility. Science has made extraordinary progress in understanding the cosmos. In just a few centuries, we've undergone a transformation in our understanding that would seem like magic to our ancestors. We've gone from thinking Earth was the center of everything, a fixed point around which the entire cosmos revolved, to mapping billions of galaxies across billions of light years. We've discovered that the universe is expanding, that space itself is stretching and carrying galaxies apart. We've detected the afterglow of the Big Bang, light that has been traveling for 13.8 billion years. We've measured the composition of the cosmos, determining that ordinary matter makes up only about 5% of everything, with dark matter and dark energy comprising the rest. We've calculated the age of the universe to remarkable precision. We've mapped the geometry of space and found it to be flat. Consider the magnitude of this achievement. A few hundred years ago, we didn't know that other galaxies existed. We thought the Milky Way was the entire universe. A few thousand years ago, we didn't know that stars were distant suns. We thought they were lights fixed to a celestial sphere. A few tens of thousands of years ago, our ancestors were painting on cave walls, looking up at the same stars we see, with no conception of what they were seeing. And now, today, we can describe the first fraction of a second after the Big Bang. We can predict the behavior of particles at energies we've never directly observed. We can theorize about what happened before there was a before, what exists beyond the edge of everything we can see. This progress gives us hope. If we've learned so much, perhaps we can learn more. Perhaps we can push our understanding further, glimpsing what lies beyond our current limits. The history of science is a history of barriers being broken, of the impossible becoming possible, of the unknowable becoming known. But here's the challenge that makes this question different from previous scientific frontiers. The further we push toward understanding what lies beyond, the more we rely on indirect evidence. We can't travel to distant galaxies. The nearest large galaxy, Andromeda, is 2.5 million light-years away. Even traveling at the speed of light, which is impossible for anything with mass, it would take 2.5 million years to get there. We can't send probes beyond the cosmic horizon. We can only observe what light and other signals bring to us, and then reason from those observations to conclusions about what we cannot see. When we talk about the multiverse, about what lies beyond the observable universe, we're engaged in a peculiar kind of science. We're using the laws of physics, validated in our observable domain through countless experiments, to extrapolate to regions we can never directly observe. This is rational. There's no reason to think the laws of physics change just because we can't see a region. The universe has shown itself to be uniform on large scales. The same physics that works here works in distant galaxies. Extrapolation is justified, but it's also uncertain in ways that everyday science is not. We might be wrong. The laws might be different out there, beyond the horizon, in ways we can't detect. Our theories might be incomplete, capturing only part of the truth. We might be making assumptions that seem reasonable, but are actually false. The history of science is also a history of confident predictions that turned out to be spectacularly wrong. Some philosophers of science argue that claims about unobservable regions aren't really science at all. Science requires testability, they say. A theory that can't be tested, that makes no predictions we can check, isn't a scientific theory. It's speculation. If we can never observe the multiverse, how can we test theories about it? Are we still doing science when we talk about eternal inflation and pocket universes? Or have we crossed a line into something else? Philosophy? Metaphysics? Sophisticated guessing? This is a legitimate concern, and it's debated vigorously in the physics community. Some of the most prominent physicists alive today disagree strongly about whether multiverse theories count as science. The debate isn't about the mathematics, which is rigorous and precise. It's about what science is and what it means to know something about reality. But I think the pessimistic view that we can never learn anything about what lies beyond is too strong. Science has always made progress by reasoning beyond the immediately observable. We reasoned about atoms centuries before we could see them. Democritus proposed that matter was made of indivisible particles around 400 BCE. We couldn't see atoms directly until the 20th century, over 2,000 years later. But the atomic theory wasn't mere speculation during all that time. It made predictions. It explained observations. It could be tested indirectly. We reasoned about black holes decades before we detected them. Einstein's equations predicted their existence in 1915. We didn't directly image a black hole until 2019, over a century later. But black holes weren't mere speculation during that century. They made predictions about gravitational waves, about the behavior of matter near them, about the light emitted by infalling gas. Those predictions could be tested. The history of science is a history of successful inference about things we couldn't directly observe. The key is indirect evidence. We might never observe other universes directly, but we might find evidence in our universe that supports or undermines multiverse theories. For example, some models of eternal inflation predict that bubble universes occasionally collide. When two bubbles nucleate close enough together, they might touch, and that collision would leave a mark. If our universe collided with another bubble universe in the distant past, it might have left a signature in the cosmic microwave background, a circular pattern with distinct temperature and polarization properties. A cosmic bruise from an ancient encounter with another reality? Astronomers have looked for such signatures. They've analyzed the cosmic microwave background in exquisite detail, searching for the telltale rings that would indicate a bubble collision. So far, none have been definitively found. There are some anomalies in the data, some patterns that don't quite fit standard predictions, but nothing conclusive. The search continues with each new dataset, each more sensitive observation. So the multiverse isn't completely unfalsifiable. It makes predictions, albeit indirect and difficult to test. Science can make progress here even if that progress is slower and more uncertain than in other areas. We might never prove the multiverse exists with the same confidence that we've proven atoms exist, but we might accumulate evidence that makes it more or less plausible. We might narrow down the possibilities, we might understand more than we do today. But let's be honest about the limits we face. Some of those limits might be absolute, imposed not by our current technology, but by the fundamental structure of reality. The cosmic horizon remains an absolute barrier. No technological advance can overcome it because it's a fundamental property of space-time, not a limitation of our instruments. If the universe is infinite, we can never map it. We can never survey it. We can never know what it contains in its entirety. We can reason statistically. We can infer that if the physics is the same everywhere, patterns must repeat over sufficient distances. We can calculate how far away our nearest duplicate might be, but we can never confirm any specific claim about what exists in unreachable regions. We can never visit, never observe, never verify. And if the multiverse exists in the form that eternal inflation suggests, if there truly are other pocket universes with different physics, we might never be able to access them or communicate with them. They're causally disconnected from us. The eternally inflating space between us and them is expanding so fast that no signal could ever cross it. Even in principle, even with physics we haven't discovered yet, no information can pass between our pocket universe and any other. And even within our own pocket universe, time itself conspires against connection. The universe isn't just expanding, it's accelerating. Dark energy is pushing galaxies apart ever faster. Eventually, every galaxy beyond our local group will vanish beyond the cosmic horizon. Future civilizations, if they exist billions of years from now, will look out at a sky containing only the merged remnant of the Milky Way and Andromeda, surrounded by perfect blackness. They might conclude they live in an island universe, alone in an infinite void, with no evidence that trillions of galaxies ever existed. The information will be gone. The light will never arrive. The expansion will have erased the evidence. This is perhaps the loneliest fate imaginable. Not just isolation in space, but isolation in time. The universe slowly forgetting itself, hiding its own vastness from any observers patient enough to wait. This is a profoundly strange situation. We might be surrounded by infinite realities, infinite variations of physics, infinite alternative histories, infinite possibilities playing out across an endless multiverse, and we might be utterly isolated from all of it. Forever. Trapped in our single bubble, able to theorize about what lies beyond, but never to see it, never to touch it, never to confirm our theories directly. But there's another perspective on this situation, one that I find more useful. Rather than lamenting what we can't know, we can marvel at what we've learned. Rather than despairing at the limits, we can celebrate how far we've come. Consider where we started. Cave dwellers looking up at stars, inventing stories about gods and heroes in the sky. We had no idea what those lights were, no idea how far away they were, no conception that they were suns like our own, orbited by planets, surrounded by the same physics that governs everything we know. We didn't know that the universe extended beyond what we could see. We didn't know that it had a history, a beginning, a future. And now, in just a few thousand years of recorded history, in just a few centuries of systematic science, we've pieced together a picture of a cosmos that stretches billions of light years. We've reconstructed its history back to a fraction of a second after its beginning. We've discovered that what we can see is just a small part of a much larger whole. We've theorized about the multiverse, about inflation, about pocket universes and quantum branches and higher dimensions. This is an astonishing achievement, perhaps the most remarkable thing our species has ever done. Future generations, if they look back on human history, might regard our era as the time when humanity first glimpsed the true scale of reality. We're like the first fish to realize there's an ocean out there, extending far beyond our little reef. We can't explore it all. We might never understand it completely, but we know it's there. And that knowledge changes everything. Let's consider what our discoveries mean for us, for our place in the cosmos, for the significance of our existence. Because these questions matter, not just intellectually, but emotionally and spiritually. Some people find the scale of the universe humbling to the point of despair. We're so small, so insignificant. A speck of dust in a cosmos that extends far beyond our comprehension. What does it matter what we do? What does anything matter in the face of such immensity? Our greatest achievements are invisible at cosmic scales. Our mightiest works will be forgotten when the sun burns out. Even our entire planet, even our entire galaxy, is less than nothing compared to the totality of existence. Understand this feeling. But I reject the conclusion that size determines significance. Yes, we're small. Yes, the universe is vast beyond imagining. But being small doesn't mean being insignificant. A diamond is small. A few carats at most, in the most impressive specimens. But we don't consider diamonds worthless because they're smaller than boulders. A poem is small. A few dozen lines, perhaps, in the greatest works. But we don't consider poetry worthless because it takes up less space than a telephone directory. A moment of kindness is small, a few seconds perhaps, easily overlooked. But we don't consider kindness worthless because it doesn't last as long as geological epochs. Size isn't the measure of value. Significance isn't determined by scale. The things that matter most to us, love and beauty and truth and meaning, don't become less important because the universe is large. And consider this remarkable fact. In all the vastness of the cosmos, as far as we know, complex life exists only here, on this small planet, around this ordinary star, in this unremarkable corner of an unremarkable galaxy. We've searched for signals from other civilizations and found nothing. We've looked for signs of life in our solar system and found none confirmed. We've discovered thousands of exoplanets and can't yet determine if any harbor life. We might not be alone in the universe. There might be other life out there, other intelligence, other civilizations asking the same questions we ask. Given the vastness of the cosmos, it would be surprising if Earth were unique. But we haven't found them yet. And if the universe is as vast as we think, if it truly extends far beyond what we can observe, life might still be extraordinarily rare. Even if there are millions of civilizations, they would be scattered across trillions of galaxies, each one isolated by the speed of light, each one alone in its cosmic neighborhood. If life is rare, then it's precious. We're not just specks of dust. We're the universe becoming aware of itself. We're matter organized into patterns that can think, feel, wonder, love. We're the cosmos asking what it is and where it came from, and what it means. That's remarkable. That's extraordinary. That's worth protecting and nurturing and celebrating. The universe might extend infinitely. There might be infinite galaxies, infinite stars, infinite planets. There might be infinite copies of you in distant regions far beyond the cosmic horizon. But that doesn't diminish the you that exists here, now, in this moment. Each instance of consciousness is its own thing, complete in itself, valuable in itself. The existence of copies doesn't reduce the original. The existence of infinity doesn't diminish the individual. So don't let the scale of the cosmos diminish you. Let it expand you instead. Let it show you how much there is to wonder at, how much to explore, how much to discover. Let it inspire you to reach beyond your current limits, to ask bigger questions, to seek deeper answers. The universe didn't have to make sense. The laws of physics could have been chaotic, inconsistent, impossible for any intelligence to understand. But they're not. The universe is remarkably comprehensible. Mathematics, invented by humans for human purposes, turns out to describe the cosmos with stunning accuracy. Equations scribbled on paper predict the behavior of particles and the evolution of galaxies. This is a gift. This is a miracle in the proper sense of the word. We live in a universe that can be understood, and we are creatures capable of understanding it. Now, let me address a final question, the deepest question of all. Why does the universe exist at all? Why is there something rather than nothing? This might be the ultimate mystery. And I have to be honest with you, we don't know the answer. After all our progress, after all our discoveries, we still don't know why there is anything at all. Some physicists say the universe exists because of physics. The laws of physics allow for the spontaneous creation of universes from nothing. Quantum fluctuations in a vacuum can create particles out of apparent emptiness. Why not entire universes? In this view, existence requires no external cause. The universe is self-caused, emerging from the mathematics of physics itself. Nothing is unstable. Something is more natural. Others say the universe exists because of a creator. But this raises its own questions. Who created the creator? We've just pushed the mystery back a level. Some philosophers argue that existence is necessary. It's more natural to exist than not to exist. Nothing is inherently unstable, a state that can't persist. Something is the default, the stable condition, what you get when you don't need anything special. This is philosophically interesting, but empirically untestable. And some say the question is meaningless. Asking why the universe exists presupposes a framework of explanation, a causal structure that might not apply to the universe itself. We ask why questions about things within the universe, but can we ask why questions about the universe as a whole? Maybe the universe just is. A brute fact. No reason, no cause, just existence, standing at the foundation of all explanation, itself unexplained. I don't know which of these answers is correct. I don't know if any of them is correct. This might be a question that human minds are not equipped to answer. Not because we're not smart enough, but because the question itself might not have the kind of answer we're seeking. We ask why as if there must be a reason, but maybe there isn't. Maybe existence just is what it is. But the mystery doesn't diminish the wonder. If anything, it enhances it. We exist. The universe exists. And we don't know why. That's humbling. That's profound. That's beautiful in its own strange way. We are mysteries contemplating a mystery, enigmas wrapped in enigmas, and even our confusion is a kind of miracle. Let me bring this journey to a close by gathering together what we've learned. We start by asking what exists beyond the universe, and we've discovered that the answer is far stranger and more magnificent than we might have imagined when we began. Beyond the observable universe lies more universe, vastly more. Inflation expanded the cosmos to scales that dwarf our cosmic horizon. What we can see, Those 93 billion light years containing 2 trillion galaxies is like a single drop in an ocean that might be infinite. We are confined by the speed of light in the age of the cosmos to see only a tiny bubble in what might be an endless sea. Beyond that, if eternal inflation is correct, lie other pocket universes, other bubbles in an endless foam, each with its own Big Bang, its own cosmic history, its own evolution from hot plasma to galaxies to whatever comes next. Some with different laws of physics, some with constants that allow complexity, perhaps even life. Most probably barren and lifeless, universes of eternal darkness or pure radiation, or collapsed singularities. But some, perhaps, harboring their own wonders, their own forms of order and beauty, and maybe even consciousness. Beyond that lies the string landscape, 10 to the 500 possible configurations of physics, a mathematical structure of staggering complexity, describing all the possible ways the extra dimensions can curl up, all the possible combinations of particles and forces and constants, and perhaps, in some sense, all of it realized somewhere in the multiverse, sampled by eternal inflation, made actual by the mathematics of existence. Beyond that lies the quantum multiverse, branches proliferating constantly, splitting off from every quantum event, creating copies of every possibility, every choice actualized somewhere, every outcome realized, an infinity of alternatives playing out in parallel, never interacting, never reuniting, each branch as real as any other. And beyond even that, we reach the limits of what physics can tell us. We reach the realm of metaphysics, of philosophy, of questions about existence itself. Questions we might never answer definitively. Questions that might not have answers in the usual sense. Why is there something rather than nothing? Why does mathematics describe reality? Why are we here to ask these questions? But here's what we know for certain. What we can hold on to amid all the uncertainty. The observable universe exists. We exist. And we can wonder about what lies beyond. That wondering is precious. It's one of the things that makes us human. It's perhaps our most remarkable quality. This drive to ask questions that may have no answers, to reach toward the unreachable, to seek understanding of the incomprehensible. The universe might extend infinitely. It might contain infinite variations, infinite possibilities, infinite realities beyond our cosmic horizon. And we're here, in this one branch, in this one pocket, on this one pale blue dot, looking up at the stars and asking the biggest questions we can imagine. We might never find complete answers. The ultimate nature of reality might forever exceed our grasp. There might always be a beyond that we cannot reach, a mystery that we cannot solve, a question that we cannot answer. The cosmic horizon might be just the first of many barriers, some physical, some conceptual, some perhaps inherent in the structure of existence itself. But the journey of exploration is valuable in itself. Every discovery, every theory, every moment of understanding brings us closer to the truth, even if the truth recedes faster than we can approach it. The act of seeking matters, regardless of what we find. The questions we ask shape who we are, even when answers elude us. So what exists beyond the universe? The honest answer is that we don't fully know. We might never fully know, but we're learning. We're piecing together clues. We're building theories and testing predictions and pushing the boundaries of what we can understand. And what we've found so far is breathtaking. Not nothing, not empty void, not the edge of reality, but more cosmos than we can imagine. more reality than we can comprehend, more existence than we ever dreamed when we first looked up at the stars and wondered what they were. The cosmic horizon is our boundary. Beyond it lies the unknown. But the unknown isn't empty. It's full of space and time and matter and energy, full of galaxies and stars and planets, full of possibilities that extend without limit, full of realities we can theorize about but never visit, never observe, never confirm directly. And somewhere in all that vastness, impossibly far away, beyond distances that make light years seem like inches, there might be other minds looking back. Other beings sitting on other planets around other stars, in other galaxies, perhaps even in other pocket universes, wondering what lies beyond their cosmic horizon. Other seekers asking the same questions we ask. Other dreamers reaching toward the same unreachable beyond. We're not alone in our wandering. Even if we're alone in our bubble, even if no signal will ever bridge the gap between us and those other minds, we share something with all possible wanderers everywhere. The drive to understand, the need to know, the courage to face the unknown and ask what's out there. This is what makes humanity remarkable. Not our size, which is insignificant, not our power, which is limited, not our lifespan, which is brief, but our curiosity, our willingness to look into the darkness and ask questions, our refusal to accept mystery as final, even when it might be final, our endless reaching toward the edge of everything. The universe doesn't owe us answers. It doesn't owe us understanding. It doesn't owe us anything at all, but it gave us minds capable of seeking. It produced, through billions of years of evolution, creatures that can contemplate their own existence and wonder about the nature of reality. That seeking, that endless reaching toward the unknown, is perhaps the most meaningful thing we do. Tonight, when you look up at the stars, remember what you've learned on this journey. Those points of light are stars in our galaxy. Nuclear furnaces burning hydrogen into helium, some of them orbited by planets, perhaps some of those planets harboring life. Beyond them lie other galaxies, billions of them, scattered across the observable universe. And beyond the farthest galaxies we can see, beyond the cosmic microwave background, beyond the limit of light itself, lies the cosmic horizon. And beyond that lies everything else. More universe than we can observe. More reality than we can fathom. More existence than we can conceive. Pocket universes and quantum branches and dimensions we can't perceive. An infinity of possibilities, perhaps stretching in every direction, in every configuration, forever. The universe is vast beyond imagining. And we're here, on a small planet, looking out into the immensity and trying to understand. That's beautiful. That's humbling. That's profoundly, remarkably human. The mystery of what lies beyond may never be fully solved, but the asking of the question is itself a kind of answer. It tells us that existence is richer than we know, that reality extends beyond our grasp, that there's always more to discover, more to wonder at, more to explore. And in the end, perhaps that's enough. Perhaps the ultimate answer to what lies beyond the universe is simply this: more. More space, more time, more matter, more energy, more possibility, more existence, more reality than any finite mind could ever encompass. The universe extends beyond our horizon. Reality extends beyond our comprehension. And we extend toward both, reaching into the unknown, seeking to understand, asking questions that have haunted humanity since we first looked up and wondered. Thank you for joining me on this journey to the edge of everything and beyond. If this exploration moved you, please consider liking and subscribing. It helps me continue creating these deep explorations of the cosmos and our place within it. The universe is vast, we are small, but our questions are infinite. And in asking them, we touch the infinite ourselves. We become part of the great mystery, participants in the unfolding of existence, conscious fragments of the cosmos wondering what we are and we came from, and what lies beyond the edge of everything we can see. Good night, and may you dream of what lies beyond.